terminando la sua introduzione.
Grazie.
Una precisazione, dovrebbe esserci Olga, ma siamo tutti numeri, quindi non c'è per la registrazione del seminario della Students Career, ma magari se viene dopo.
Va bene.
Ok, a dopo, grazie.
Ma mando da te eventualmente.
No, io poi ritorno per prendere il tutto, quindi se è venuta magari poi la registro, ma se non c'è...
Ok.
Grazie.
Okay, I think we can start. It's my big pleasure to introduce to you Michele Focchi. Michele is a very good friend of ours. He has been with us for 3 years, up to last year, yes. And he has received his PhD from the Italian Institute of Technology, and he has worked with them for quite a long time. Then he came to us for a 3-year postdoctoral experience, and now he is consultant for a startup company located in London. And it's also my big pleasure to announce that he will soon join also our faculty. He will become a faculty member of my department, of our department, starting from the 15th of this month. And so Michele is renowned for his research on quadrupeds and other type of robots, but I think he will give us a much wider perspective on his work throughout the last decade, I guess. And my big pleasure to be with you. Thank you, Michele.
Thank you very much, Luigi, for the invitation. Yes, unfortunately, my production is very big in terms of research, so I have to select only two topics. You already went through my academic journey already, so I won't delve too much into that. Let's start from the title of this talk, which is a synergetic view to increase mobility awareness of mobile robot. So the overarching goal is to make, or my research is to make mobile robots autonomous, increasing the awareness of motion. What does it mean this? To achieve this, for example, we need different topics, to cover different topics from different fields, from control, we need a planner that generates trajectories based on the environment that is perceived, and a controller to track these trajectories and reject disturbances. We need some visibility metrics to know when we are about to violate the physical constraints of robots, of mobile robots. In my case, I was working with quadrupeds, so I had many constraints, from friction, actuation, and kinematic constraints. Finally, also state estimation. It's important to feedback the state of the robot that might not be always observable. In this talk, finally, the last topic is about, last ingredient is mechanical design, because a smart mechanical design can massively simplify the effort of the controller in achieving our desired goal. In this talk I will focus mostly on these two topics, on control and planning, and specifically I will talk about a few examples of new robots, mobile robots, that one is a climbing robot that I presented last year, actually is on the final prototype, so I will present the whole development of the idea. This is quite educational purpose, from the starting initial idea to the final prototype, and also another work on reinforcement learning, quadruped jump, so making a quadruped learn to jump using reinforcement learning techniques. First, let me give you a few motivation on why using climbing robots. They have a number of applications ranging from bridge structural inspections that nowadays are done by humans with expensive scaffolding structures, cleaning of glass surfaces, especially for skyscraper or high-rise buildings, and also recently they've been employed in maintenance on wind turbine profiles. Other application could be exploration of remote areas and rescue, bringing first aid in rescue missions. But the killer application that I foresee for this class of robots is what is related to maintenance operations in the heights, in the wall. And this has not been explored yet, and this ranges from setting anchors to remove dangerous and unstable boulders from the rock. The motivation is that mountain environments are becoming more and more delicate, vulnerable to climate changes, and often there are landslides, there are rock collapsing due to the higher temperature that can make small villages under the rock wall in danger and jeopardize tourism. We have here landslides on Rente Cosmics, which is a mountain that I climbed myself 15 years ago. And this is some live recording that were very big stones falling down. So constant monitoring and it's needed. Sorry, I will try to do this. Constant monitoring is needed. See if you can.
It's not here. Okay.
Just 1 second.
Yeah, the cross. Just
okay, that's it. Constant monitoring is needed, a maintenance activity to actually monitor the environmental condition and health of the rock walls. But this area of interest are difficult to reach, and the maintenance operations are dangerous because they're mostly done by alpine guides or skilled personnel that are accessing this area, remote area, through mountaineering technique and executing operations, maintenance operations while hanging from a rope. And of course, there are not many alpine guides around, so there is a scarcity of skilled personnel, inherent danger, and also the vibration exposure these workers are exposed to. It should be limited by law. So this suggests the application of a robotic solution for this kind of application. What are the requirements? So whenever we come up with a need and we just motivated the need of this application, we come up to find some requirement to develop the ideas. And what could be the application requirement that are out of reach from the other solutions that are mostly done by drones or robots that are crawling very slowly on the wall. First, they should carry heavy payload, and this is, for example, not possible from drones. With drones, and maintain a stationary position to perform a maintenance operation for a long time. They should be able to move quickly and efficiently on the wall, and also be able to overcome large obstacles along the way. For example, in case you have bushes, you have obstacles, trees that you need to avoid. And first, they need to be able to autonomously or semi-autonomously perform maintenance operations. For example, drilling, expanding, injection of expanding foam injection, expanding foam injection, or debris removal. The concept is that this robot should be able to move vertically, horizontally, and also to be able to avoid the obstacle, enable some detaching from the rock wall. because the rock wall, as I said, is not a flat surface. It is very rough and there's many obstacles. Therefore, to be able to avoid obstacle, we need this ability to jump, to detach from the wall. So taking inspiration from human climbers, we propose a robotic solution that is able to move and reach target along steep mountain walls by exploiting a combination of two ropes that can pull up or the structure upward or by some winches mechanism, so they can wind and unwind the rope and be able to reach any position on the wall, and a retractable leg. And the retractable leg is like a leg, actuated leg that can push on the wall, initiating the jump. Finally, there could be added some propellers to attach it to the base to control the orientation. We will see later. Once landing, to avoid that the robot crashes on the wall in a bad way or tips over, it might be needed a landing mechanism to be able to dissipate the excess of kinetic energy. The first idea was to use only one rope. So we came up with this robot with a single rope. So as I said, research is could be an iterative process. It means that you devise a solution, then you test it, and you find out that it's not optimal one, so you want to do another iteration. And this is very normal in the process of designing a new idea. And the problem of this single rope solution is that limited massively the reachability of the lateral target. You see, the optimization that we see, we carry out the motion for the jump was requiring a lot of effort from the electrical motor driving the hoist, the winches, to get out from the friction cone, from the region limited by the friction cone. So instead, the two-rope solution, adding another rope with another anchor point, both attached to the to the robot, enables to relieve this problem and solve this issue. And all the points could be reached ideally, given that the actuators are strong enough in the space between the two anchor points. This solution enables us to satisfy all the requirements, because, for example, engaging brakes, if we put brakes on the hoist, keeping the ropes in a certain position, we are able to keep any stationary position on the wall without consuming significant energy. So we satisfy requirement 1. Requirement 2 was about being able to move quickly and efficiently, and mixing with lateral and vertical motion, we are able to move very fast, taking jumps. And taking jumps also allows us to swing over the wall and overcoming the obstacles. Finally, a landing mechanism allows the robot to dissipate the kinetic energy and stay firm on the wall and be stable to perform maintenance operation, which was the fourth requirement. However, there are several scientific challenges in this robot. First, the first one related to the dynamics, which is non-linear, underactuated. Underactuated means that it cannot control fully its state. For example, we cannot control whenever in flight, we cannot control the position of the robot in the direction perpendicular to the robot plane. And is hybrid. It means that it could have a discontinuous change between whenever in contact or not in contact. We have feasibility constraints which are related to the friction constraints. For example, when the leg is touching the wall, it can slip if the tangential force is too big. Unilateral constraints, which means that the leg can only push and not pull on the wall. And actuation limits, both on the rope and on the leg. And the kinematic limits, of course, we cannot extend the rope and the leg in a infinite way. We have some range. The controllability challenges are related to this unilateral constraint. So, as I said, the leg is pushing, but it's also pushing in a very quick way, so in an impulsive way. In a few tenths of milliseconds, it should be able to completely extend. This creates some issues in mathematical implementation of the optimal control problem that we will see later. And the ropes should be able to develop force, but this force should be always a pulling force. So it could be that if you don't properly plan the trajectory, the rope can be untied. So it can get a slack and you lose completely the controllability on the road. We should be able to deal with irregular and varying terrain and avoiding natural obstacles, so we do to consider this in the optimization. And finally, because we have two ropes, we have a kinematic loop. What is a kinematic loop? Is a constraint that tells us that the rope lengths cannot change independently one from each other, because their attachment point needs to be on the rope. So the changing length on one rope is not independent, cannot be set independently from the other one. And all these challenges makes this system a good candidate to apply optimal control techniques for motion planning. This is the modeling of the system. In the full model, we have to implement optimal control, we need a model of the system, and we see on the left the full model, 50 degrees of freedom of the system that we use in simulation, okay? But to be able to optimize in an efficient way and don't take too much time to solve the optimization, it's good to have a reduced order model. A reduced order model is a model that captures the main dynamic of the robot. In this case, we neglect the angular dynamic. We only consider the mass concentrated, the robot as a point mass with the mass concentrated at its center of mass. We have a few assumptions. The ropes are inextensible, they can only pull, but they are not elastic. And this enables us to boil down the representation of the robot state, robot dynamics, using only three generalized coordinates, which are psi, which is the angle between the rope plane and the wall, okay, and the length L1 and 2 of the two ropes. The advantage of this kind of parameterization, there are possible also that other parameterization, for example, the position x, y, z of the point mass, is that allows us to fulfill by construction the kinematic constraints that here we have to be enforced explicitly. The famous kinematic loop. And this is the model is a point mass, so we have the Newton equation, we have acceleration times mass, minus gravity. We have the force of the first rope, and this is the axis, the direction of the axis of the first rope, and the direction of the axis of the second rope, and the force of the applied by the leg. From forward kinematics, we can link the position of the robot to the generalized coordinates, psi L1 and 2, and differentiating twice, we can replace the p dot dot with acceleration of the state variables. And so this is the reducer, the dynamic equation, the first second order differential equation that represents the reducer order model that we will use in the optimization. We set up the optimization, the optimal control problem to find the optimal jump between 2 points. Because we employ a direct approach to implement optimal control problems, so we transform the optimal control problem in a numerical optimization nonlinear problem, and we use single shooting transcription to integrate the dynamics. given only the inputs as decision variables. And we do this for the whole duration of the horizon. Well, the duration of the horizon is also a optimization variables, which is TF. So it's the duration of the jumping trajectories. States, as you said, we choose the state of the reduced model, order model, and the derivatives, and the equality constraints that is not really an equality constraint because you use multiple shooting, single shooting. We have the reducer of the model dynamics. We have the as control inputs. We have the flag, which is an impulsive nature, and the pattern of rope forces for the left and the right rope, so along the whole horizon. The objective in the cost function of our nonlinear problem has two terms. One is the smoothing of the amplitude of the forces, of the rope forces, and the other one is the minimization of the work. So we don't want to consume too much energy, we don't want the rope forces to change abruptly. Then we have several constraints that are, for example, the fact that we have bounce. Remember the unilaterality constraints on the rope forces. The rope can only pull and not push, otherwise it gets untight. Limited actuation forces on the prismatic leg, and friction constraints. So the tangential force. This is a projection of the force on the tangential direction, should be lower than the friction coefficient times the normal force. This is the normal force. Otherwise there is slippage, so we lose the controllability of pushing the level move. Finally, these are two constraints that are telling us that, for example, the motion should be on one side of the wall and not inside, and we can define whatever generic obstacles, for example, a rock pillar, to avoid as a function of the state. So it's a path constraint actually. Looking closely to the taxonomy of jump, we have the thrusting phase where the prismatic leg pushes in less than 200 milliseconds. The robot away from the wall to initiate the jump. We have the flying phase in which we have the rope forces that are given, the optimized rope forces profile that are given to the rope to create a motion while flying and land to the desired location. While on top we can have we see a controller that corrects the mismatches that can be happen due to disturbances. In addition, we can have an orientation control system that also corrects the orientation of the robot, because remember, we are not considering the orientation in our optimization. Finally, the last phase is the landing phase, also very short, where the robot lands on the wall and try to dissipate the kinetic energy without rebouncing, okay? Because if we rebounce or tipping over, the robot loses the landing target. We can have, we see also, propellers that can be activated to push the robot against the wall to increase the normal force. And why this is important? Because for drilling operation, the drilling operation requires a lot of normal force to be able to percussion drilling to break the rock basically. And if you're almost vertical, you're not able to drill because the only normal force comes from the component of the gravity vector, okay? So this is a way to circumvent that issue. We didn't think at the beginning, this idea came later on in the process of the project. So how do we embed, how do we port the result of the optimal control of optimization that is done on the reducer order model into the real robot, into the full model that we model is in gazebo using, for example, 2 passive rotational joints for the anchor point, like a rolling pitch joint, and 3 passive one on the attachment point of the rope. And we have an active prismatic joint that models the rope. Okay, and we can directly apply the force profile to these prismatic joints. The leg has a little bit of issue because the optimization provides an F leg that is applied to the center of mass and not to the tip of the foot. Okay, so we have the leg is driven by 3 joints: one hip pitch, hip roll, and a knee extension. Okay, prismatic one. So 2 rotational and 1 prismatic. And we should use the full dynamic equation of the robot to map the F leg into forces on the prismatic and 2 rotational joints. We try to align the F leg. We try to align the leg to the direction of the F leg. Why we want to do this? Because if we have the F leg not aligned, we could create a moment around the center of mass that once the robot is flying will initiate a pivoting moment, a pivoting motion of the robot, and we then land with an orientation that is not desirable. In terms of disturbances to be used in a real application, a robot must be able to overcome and compensate and reject disturbances that are coming from the environment. In a case of a climbing robot, what are these disturbances? Rockfall, and these are, for example, impulsive disturbances coming from the top mostly, and the wind. And wind, which kind of disturbance is a constant disturbance. If there are disturbances, the trajectory planning is no longer optimal, and the robot, if we don't compensate them, could land in a wrong location with respect to the desired one. Therefore, the strategy to compensate disturbances is that we devised is a model predictive control strategy that every loop optimizes real-time the pattern of forces. So we keep the original optimization coming from the offline optimization that we solved before starting the jump, and we adjust it according to the error in the robot base. But we can adjust disturbances, we will see in the next slide, only on the rope plane with the ropes and not in a direction perpendicular to the rope plane. So for this direction we have a propellers, and we activate or deactivate a propeller to correct the disturbance. So if you see here, we have a reference motion, which is the red one for the free state variables. And in the case of non-MPC, MPC is off, you see that when there is a contact disturbances, there is a massive error on the state variable. Okay, and this is an impulsive disturbance. You see the impulse is even creating a bigger error. In the case we have MPC for the ropes, we have perfect tracking for L1, L2. And also in the case of the impulsive disturbance, you have an initial transient and then you recover and you have no error at the end, but you still have error on the direction perpendicular to the rope plane, which is represented by the psi, okay? So in the propellers, we are able also to completely reject, in the case of constant and impulsive disturbance, any kind of disturbances for the free state variables. These are the simulation results. You can see this is the rope in red, the leg impulse in blue, and you have the robot achieving the landing location, which is represented by this red ball, while these are the 2 anchor points. This is the test for the obstacle avoidance. You see the intervention of the blue of the propeller as well from the blue road. This is from underneath. You might not be able to overcome the obstacle in one jump, so you might take intermediate jumps, for example. And this is showing that the approach works for whatever wall inclination. You could have upward jumps with different wall inclination or downward jump with different wall inclinations. Landing strategy, having only one leg to push, the robot is not able to stabilize itself to perform anti-rotation, so we thought about adding two legs driven by revolute joints that are creating this landing mechanism. During the flight, the thrusting leg is retracted and the two wings, the two landing legs are extended to manage the landing. The impact energy is dissipated implementing a Cartesian impedance, okay, in this direction, where the critical damping in Cartesian impedance is set, we set the damping to a critical damping value, and this avoids the overshoot of the velocity, and so it avoids the change inside of the base velocity and the bouncing of the robot. We added two wheels to the tip of the landing legs to avoid the creation of internal forces, so to create horizontal forces because could jeopardize the emulation of the Cartesian impedance. But, and this is the landing test, you see that this is in the Cartesian variables, so the robot in the x direction is in the direction out of the wall. Whenever it lands back, it remains there and without rebouncing. Maintenance operations, once we reach the target, the robot is ready to perform maintenance operation. For example, drilling, loose rock removal, or injection of resin. But these operations involves the application of forces on the robot itself. So this, the forces due to drilling, unless we do something, could be to create, make the robot tip over, for example, or lose the contact with the ground. So we need to do a more I want to also close this one. Principal static analysis. And whatever operation we want to perform, for example, drilling, we need to estimate the maximum force that we are able to exert on the rock. And for this, we use computation analysis tools. For example, this feasible branch polytope that we proposed in 2018 is used nowadays in many quadruped robots research studies. That tells us the polytope, so the convex set of feasible forces that we are able to apply, that we are able to withstand without violating some of the constraints, which are the unilateral constraints of the rope and the friction cones, and also the unilateral constraints on the feet, on the landing legs. And this branch polytope is a compact representation of these constraints. And once we decide the loading direction, for example, drilling normal to the wall, we have different maximum forces that depends on the wall inclination. Of course, if you are on a slab, on a less inclined wall, we have the gravity that help us in drilling, so we can achieve higher forces, and also depending on the position of the robot. So if these are the left anchor and right anchor, if you are in the middle, you are able to withstand higher forces. Finally, and this is something an idea that came from the reviewer that revised the manuscript paper that we wrote. They told us, but why don't you use the wheels for maneuvering on the wall? And this is exactly virtuous outcome of good work done by a scientific community that feedbacks on reviews possible improvement of the papers. And so we added this control of the wheelhead were passive before, but we tried to, once landed, to activate, and this unlock thousands of possibility because you can exploit easily planning and control technique for wheeled robots to move on the wall in the part of the wall that are clear from obstacles. So if you have a slab sufficiently free from obstacle, we can move with the wheels more efficiently. And finally, this is a real prototype that is on construction by two of my students, Luca Ardonc and Ruben Malacarne, which are here in the audience. And on the right, we have the CAD design. We have the 2 winches and the robot, and these are the ropes. And the real prototype sketch is on the left. In this case, they decided to implement impulsive motion, exploiting a pneumatic piston that takes pressure from a high pressurized gas bottle, while they embedded the brakes and the batteries in the winch. So if we have batteries in the winch, we don't have to put on the robot because we can supply the energy to the robot through the cable that are properly coated. And so we reduce the inertia and improve energy efficiency. And this is a video of the system. Very early. Tests. Finally, regarding the orientation control system I mentioned before, we found out a configuration of propellers or unidirectional sources of thrust that enables us to do all the forces we need to control the orientation. And we need to control orientation during the flight because the robot could rotate and not land aligned with the wall. We could control the orientation of landing, so think about removing the landing legs. If we have a way to apply forces on the robot once landed, we can avoid the tipping over. And so we simplify the design of the system, and the prototype, the actual system becomes cheaper and more easy to maintain. And finally, what we mentioned to apply normal forces to increase the normal force on the wall for drilling. Monodirectional thrusters can be duct propellers that are more efficient, or even cold gas thrusters. And this is under a patent application, solutions. And future works are related to also possible operation mode for the Alpine platform. Think about a geologist that stays at the bottom of the valley, sends a drone to acquire a 3D map of the rock wall, then decide on a tablet what are the points of interest to be achieved for maintenance operation or for inspection or for monitoring, and then these are targets that are becoming references for the optimization, and the robot will go there. Then we can decide to, with a VR headset, to see the real-time, teleoperate the robot in real time and see the map, the condition of the wall in real time. And then you can decide to, as I said, to teleoperate or to apply a certain predefined maintenance operation. Take-home messages: we presented a robotic platform that can perform maintenance operation in a mountain environment, either maximum vertical or slanted. It cannot be overhanging, of course. We propose an approach to plan optimal omnidirectional jump trajectory while avoiding obstacles. And we show that an approach for which the robot is able to track reference trajectory and achieve high landing accuracy even in face of disturbances. And showed also preliminary testing on the real prototype. The code is available, open source, you can try it yourself. Okay, we are exactly half of the presentation. We are a bit late. No, let's say not half, 40%, 60%. The second topic is related to the reinforcement learning for quadruped robots. First, why we care about quadruped robots on a first instance, because they are able to, better than wheeled robot in uneven terrain and rough terrain, they can offer high stability with respect to humanoids, because they have a big quadruped platform. They are able to adapt to quickly and predictable changing environments. They can be used in search and rescue operation, exploration, and industrial inspections. And why do we need jumps? Because there are some situations, for example, in which the usual classic gait pattern, like trot and walk, the quadruped use, are not sufficient to overcome certain obstacles that are bigger than the leg extension, the size of the leg of the robot. In these cases, being able to initiate a jumping motion could be the solution. We, as in the previous case, can split the jump in the three phases: thrusting, flight phase, and landing phase, and we highlight the two important moments in the jump phases that are lift-off moment, when a robot leaves the ground, and touchdown when it comes back on the ground. If you see a real quadruped, a real dog, we see that we have, say, the composition. Now, why jump is difficult? Because it requires quite demanding motion in terms of timing. Its duration is very short, but also in terms of pushing the limits of the robot. So we need to consider many constraints. First, the extension of the leg is limited. We cannot extend more than a certain quantity. Joint velocity, they cannot extend too fast. We have torque limits. You cannot apply too much force on the joint, and extend forces. No, this should not be there. Sorry. Environmental constraints. Again, the terrain could be as a certain capability of resisting the force, the tangential force we apply before slipping. So we cannot apply whatever force we want. And also, even if we have the torque capacity, dynamic constraints, where once we are in the air, we have conservation of momentum, and we cannot, we lose controllability on the robot. How jumping is tackled in the state of the art and has been tackled in the state of the art until now. We have optimization-based method that, as I said, they are time-intensive computation. They cannot be implemented real time, or very difficult to be implemented real time. They are subject to local minima. The advantage is that their result is predictable, so it's guaranteeing the satisfaction of the constraints, or the physical constraints of the robot. And of course, it's more accurate if you use the free body dynamics than using a reduced dynamics, a reduced order model of the dynamics, but more computationally intensive. But in the case of the jump, it requires the introduction of artificial constraints. This means prefixed contact sequences and fixed time of flight. For example, we know to avoid that the system becomes a mixed integral optimization problem, we predefine the duration of the thrusting phase, the flying phase, and the landing phase. But of course, you can have issues because you can land in an instant that is not different from the one that you planned with optimization, and this then creates issues. The other approach is reinforcement learning, in which we learn direct control of the robot by trial and error. So we learn how to apply the forces or the joint reference position to achieve the jump without any prior knowledge. The result is unpredictable, so there is no guarantee that we are exactly satisfy the friction constraints. For example, requires intensive training and computation, many days or hours of computation to train the system. And but the advantage is that enables real-time execution, because Usually this approach is involve the training on a neural network, which is just a matter of multiplication of weights that can happen in a matter of milliseconds. The solutions that they provide are not always feasible. So, as I said, they could violate the constraints. Reinforcement learning is a branch of machine learning that studies the training of agents capable of learning an optimal behavior, in this case the best jumping motion, while interacting by trial and error with an environment and receiving rewards from the environment. So we have the target, the goal, which in our case is the target location. We have agent that provides an action, okay, that is in some way should be able to codify, realize the jumping motion. And then we have the simulator that simulates the jumping motion, and according to how good he landed or he managed to land close to the target, we have a reward that is fed back to the agent to learn a better action. So the action represents a decision taken by the agent based on its current state. In our case, the state is mainly the target. So we are here and we want to go to jump there. So the delta in terms of jump from the actual state configuration. The reward is a quantitative measure provided by the environment as feedback. Once talking with a colleague, I was thinking about, but how come that animals like deer or very quadruped that are learning to walk very quickly once born, and I replied myself, maybe these animals have some hardwired mechanism in their brain. On one side, they have low versatility because, for example, a deer is able to walk, to jump, but is not able to, like a human, to do different jobs, be an astronaut, football player. So human baby is able to learn many more things, is more versatile, but it requires a long training time before learning all these different capabilities. Quadruped baby newborn is very fast to learn, very simple, not complex, but is quadruped capability, locomotion capability, but has low versatility. And that suggests me that a certain level of structure in the neural network should speed up learning. And I started from that to implement this force jumping motion. And the idea is to guide the reinforcement learning using some domain knowledge. So this enables us in a certain way to merge the two worlds, optimization-based approaches and end-to-end reinforcement learning approach, getting a common ground. The assumption, the guided reinforcement learning, it means that we can exploit physical knowledge, making some, allowing us to do some assumption that can drastically reduce the search space. And this is added as a structure to the learning system by model-based prior knowledge. And at the same time enables real-time execution, enables us to have a result that is more predictable than the classical end-to-end learning approach, and reduce the training time in terms of sample efficiency. Increase the sample efficiency. First, how to reduce the search space dimension? We reduce the action. Okay, we cannot apply whatever joint, position or torque we want every loop, but we do some observation coming from the physics. The first observation is that the jump trajectory lies in the vertical plane connecting the takeoff position to the desired target location. This means that the feasible velocities also are constrained to the same plane. And this means that we can restrict the coordinate to describe the jump to a convex bidimensional space. This enables us already to reduce the dimension. So if you're considering only position, not orientation, is already from 3 to 2. Then, another observation, during the flight, there is no longer the thrust. And the jump trajectory, we said, follow the conservation of linear and angular momentum. And this means it follows the ballistic motion of a projectile. This allows us to link the jump target location to the liftoff location, because we know this is a projectile equation that links them. And so we can concentrate to plan the trajectory only for the thrusting phase. Okay? So we care only what happens between here and here. Then this is the projectile equation. And but once we arrive at the liftoff moment, we have infinite combination of vertical and horizontal velocity that allow to reach the same target. For example, you can do a very high vertical velocity for a long time with a low horizontal velocity to reach the target, or we can do a very high horizontal velocity with a low vertical velocity and reach the same target. But of course, the time of the jump will be different. So among the infinite solutions, we want to find the optimal one that satisfies also the physical constraints, because we have the constraints on the robot to satisfy. How to implement this trajectory? How can we further simplify? Could be whatever trajectory. We know that we want to link the actual position to the liftoff position. So we want to find the liftoff position and velocity. And if we look at the animals, they have a compression phase whenever they jump and an extension phase. The compression is to enable the robot to exploit the full range of the joints for the vertical acceleration or forward acceleration of the center of mass. And we found out that this trajectory has this shape, more or less. Of course, it can be different depending on the kind of target, but is easily parameterizable by the third-order Bézier curve. The third-order Bézier curve has advantageous parameterization because the derivative is very simple to compute and is defined by control point. In the convex hull, so is defined in the convex combination of the control point. So it's quite easy to visualize as well, and we can link the Bézier curve that connects the center of mass to the liftoff position, and changing the parameter of these curves, the curve changes, and so changes the liftoff the velocity. See? So this is the reinforcement learning schematics. We used TD3 or PPO algorithm to train in simulation the RL policy, and the action is basically contains the parameters of the Bézier curve that will end up in a certain liftoff velocity and position of the center of mass, and so in a certain target location, and the thrust duration. So we are able to, differently from optimization, we are also able to optimize the duration. The reward function will be engineered using domain knowledge to obtain feasible jumps. For example, satisfy the physical constraints and penalize the landing error. So we want to land close to the target. So there are two terms in this reward. The first term is negative, okay, and penalize whatever in the simulation the force violate the unilaterality constraints, so there are forces that are entering the ground, or the joint torque limits are violated, the joint limits are violated, friction limits, singularity that exists too extended, and or the robot is not able to lift off. So we want to discourage the fact that the robot just do little jumps to reach the target, because this is a possibility if you don't tell him via a reward the the reinforcement learning process will find that solution. On the other hand, we want to encourage with a positive reward the achievement of the target. So how close the center of mass arrive to the desired location. And this is done with this function. It's very simple. This exponential is a negative exponential, and it will be 1 whenever target, sorry, this is a touchdown, sorry, this is an error. So whenever the touchdown, whenever the robot lands, is equal to the desired target. Okay, this goes to 0, exponential goes to 1, and so it achieves its maximum values. Then you have a second term that tells us how long is the jump. Of course, if you have a landing error of 5 centimeters on a jump of 1 meter, is a good. We need to give a high reward. If you have a 1 centimeter, 2 centimeter error in a jump of 2 centimeters, it is not that good. So this also premiate basically give a higher reward for longer jumps. Then we put this, we multiply the R positive with this exponential of R negative. So we want to be able to have R negative to 0. So we want to have the all constraint satisfied, physical constraint satisfied, to have to evaluate the positive reward internally. First, we did the training on a simple monopod, so we could get a read of the orientation, and we just consider linear motion. And we see that after 20, we see the jumping capability improve with the number of training episodes and reaching a good accuracy even after 20,000 episodes. Then we did also, we showed the capability of generalizing of the neural network, asking for targets out of the training region. So this is the test region, for example, and this enables to show that the robot is pushing the performance limits to achieve that target. The other important point is that the training is also able to learn the controller inaccuracy. We use on purpose a very crude rudimental controller, a PD control price gravity compensation, and this controller of course has some limited tracking performances, and we see that the blue ball is the target location and the gray ball is the ideal landing location that you would have if you track the action. So on purpose, the neural network, the agent, is creating an action different from the target one, such that knowing that the controller will not be able to track perfectly this action, will land on the desired target. Then we have we moved to quadruped, and we parallelized the simulation. Thanks to the availability of a GPU card, we exploit that to accelerate the training of the neural network. In particular, we use a framework, Orbit, and Isaac Jim simulation environment to train a neural network running 4,000 simulation of robots jumping in parallel. And all this robot experience contributed by all this robot are contributed to the training of a central neural network, reducing a lot the amount of training episodes. In the case of quadruped, differently from the monopod, we are also having orientation, so we included in the action not only the lift-off center of mass and the lift-off center of mass position and velocity, but also the lift-off orientation state, so position, angular position, and angular velocity. The training required only 10 hours and only 2,000 episodes, because we're running 4,000 optimization in parallel, simulation in parallel. to learn omnidirectional jump in a even higher cuboid region. Note that we are also learning downward and upward jump. So the jump is not only omnidirectional in XY direction, but it's also on the vertical direction. So downward jump and upward jumps. And we see that we have a training convergence after 2000 episodes. And this is a dramatic reduction of the learning phase with respect to end-to-end approaches, because, for example, end-to-end approaches can take up to 33,000 episodes to converge, showcasing that our guided reinforcement learning is more sample efficient. Additionally, end-to-end approaches are very hard to implement because they need a lot of reward engineering. I tried myself to implement an end-to-end approach for comparison for 1 year, and I didn't manage. Here are the results. To learn how to jump on a higher terrain or a lower terrain, we basically create a platform that moves with the robot in the target, elevated target, for example. Sorry, it's not flat terrain, it's on terrain of different heights. And here are the first experiment on here University of Trento with the Aliengo robot. An important feature of this approach is that when doing experiments, we found very difficult to estimate the apex of the robot, because we usually use accelerometer, we integrate it, we get the vertical velocity, and we see when the vertical velocity changes sign. But accelerometers are low quality, they are biased, they are noisy, and the fact that we have an initial acceleration, the jump duration is very short, very less than half a second, makes difficult to have a good estimation. On the other hand, the touchdown instant is estimated from the contact forces, which is on its behalf estimated through joint torques. And what happened is that you could have, during the retraction phase, after the thrusting, we were retracting the leg and extending them. Okay, whenever we were retracting, we were creating a fake acceleration that triggers the apex too early. And whenever we were extending, we created fake forces because the model was not perfect, that triggers the touchdown or too early or not at all. So we were able to jump but not to land. And the solution was to exploit the fact that our guided reinforcement learning action actually is model-based, is providing a ballistic equation, an input for a ballistic equation that can enable us to predict the ballistic motion and estimate from that the apex and the touchdown instant beforehand. So we were just applying that, and from the first trial, the jump worked smoothly. We also did zero-shot evaluation of the without retraining policy on another platform, for example, a Go1 robot. And we see that more or less the jump is working. And this is enabled by the fact that we are learning the action in the task space. So we are having a lift-off center of mass location and a trajectory that is tracked by a low-level controller. And this makes the approach platform independent. We are not providing joint states, so you don't have to retrain from scratch for each robot. One advantage approach with respect to state-of-the-art is our approach is very, very accurate. We're able to use a policy trained for 4 motions from 0 to 1.2 meters. And we see that we have for 0.8 meter, 80 centimeter, we have an error which is very low, below 5 centimeters. And this is instead a policy trained for omnidirectional jumps, so it's less performant in a single forward direction, but works more or less for every direction. Take-home messages: guided reinforcement learning is a strategy used for jump, enables us to generate accurate omnidirectional jump on different terrains of different heights. The jump in trajectory is computed in a few milliseconds, so the advantage of real time, and is more sample efficient than the end-to-end RL, avoiding complex multi-stage reward engineering. The learning process is also able to learn controller inaccuracy, and having a task-based action enables zero-shot evaluation of different platforms with the same morphology. Of course, you cannot use that on Hexapod. Finally, enables model-based estimation of apex and touchdown from landing. These are the collaboration established along the years, which, in case you are interested to do a master or a thesis or a PhD with me, can be possible places to do an exchange. And the presentation is finished. I'm glad to reply to your question. Also, if there are questions from the audience,
yes,
online. Yeah.
Can you get on the slide just yes? You talked about zero-shot evaluation, and I didn't really understand what that means by that. But what do you mean by that?
We trained the policy for the Alien robot. Then we tried the same thing with the Go 1 robot, which is a robot that is 12 kilograms instead of 21, 22.
Okay. Because the control you give the robot is just the...
It's a kinematic trajectory. So the fact that you have an underlying control to track it allows us to use it with different platforms.
So you're relying on the platform to understand this kinetic curve, and
of course you need to map it. I didn't say that this trajectory needs to be converted into joint trajectories by inverse kinematics that, of course, will be dependent on the platform itself. Yes, the controller is an impedance controller, joint space impedance controller plus a gravity compensation. So, of course, the gravity compensation needs to be adapted to the heavier robot.
It's like that E2E paper used 23,000 training steps. Is it not because they maybe didn't use like the parallelization used in this one?
No, they use the same parallelization of 1,000 robots.
Okay.
What they do is that they are continuously changing an episode. We have only one step at the end of the episode. So we do one jump and we check wherever is landed and compute the reward and do the training step for each episode. Their episode is, since they are continuously sending joint positions, it's taking more steps. Okay, and they do a training episodes every 24 samples, I think. But maybe this is just 200 milliseconds. So there is a difference in terms of episode length. So the training duration, due to the fact that this episode simulation takes time, it could be different. But we need less number of samples to train to learn to jump with respect to them, because they need to have 23,000 and we have only 2,000. Then, of course, the time it could be comparable. Okay. Any question for the audience? Okay, that's it. Thank you very much. Abbiamo registrato.
Sì.